Okay, hi distance learners. It is Tuesday. What's the date? 29th. September 29th. We're moving on in our functions unit. So last time we talked about evaluating functions, and we talked about how you can put a value in and get a different value out. So we did these 2 pages in our notebooks. Why am I frozen? Why are you frozen? Just hang in there, distance learners. I'm figuring it out. Okay, so we did these 2 pages, and then the next lesson is supposed to be composite functions, but we're going to skip that. Don't murder it, because we might come back to it. Just skip page 16. So what we're moving on to today is graphs, which hopefully some of you guys are going, what? Because we go from plugging in all of these values to a function, and now all of a sudden we're graphing. So I brought you a worksheet that's going to help you, or help me, show you how these 2 things are related. If you don't have one, they're over here by the whiteboard. So this is our first graph that we're going to talk about, and hopefully he looks really familiar to you guys. He's a parabola. Does that sound familiar? He's a parabola. And he has this thing right here called a vertex. His vertex is at 0, 0. So he looks like kind of like a U. If you folded it in half, he would line up perfectly because he's symmetric. And hopefully you talked about him a lot last year and maybe saw him in 9th grade. So this is our thing that we call a parabola. Now, we are going to take this parabola. Sorry, I should tell you his function. His function is y equals x squared. We're going to take this function and plug some values into it. So last time we reviewed how we take those values and plug them in and get out a new value. And today we are going to plug those values into a function. And we are going to graph the values that we get. So I'm going to tell you what numbers we're going to plug in. We're going to plug in -1, just kidding, -3, -2, -1, 0, 1, 2, 3. And because this is an x squared, we're going to want to make sure that we use parentheses. Our function is x squared plus 3. So in this line right here, we're going to plug in -3 squared plus 3. So whatever calculator I'm using, I'll just use this big one. I'm going to plug in -3 squared plus 3, and I'm getting 12. So 12 is what I'm going to put in the y column. And now I can put those together to make a point on a graph. This was the x that I plugged in and the y that I got out. So if I want to plot this on the graph that's down below, I go to my x-axis, left to -3, and then I go on my y-axis up to 12, which isn't really on the graph, so we just have to kind of eyeball it. That's our first point. Okay, back up to the table. The next thing that we're plugging in is -2 squared plus 3. So you guys plug that in. I'll just call on somebody to give it to me. You got about 10. 3. 2. Okay, Bailey, what did you get? 7. So this time we plugged in a -2 and the function gave us 7. So this is what we did last time. Now we're going to use those values to put a point on this graph. So we go left -2 and up to 7. Okay. Next is -1 squared plus 3. You plug that in, I'll just pull somebody's name again. You got about 10. 2. Okay, it goes to Brianna. She learns at home. Hopefully you can answer that. Jaden. No, Jaden. Elijah. 4. So plug in a -1, get out a 4. So down here, we start at 0, 0, because that's where we always start at the origin. We go to the left 1, and then up to 4. Okay, now we're plugging in 0. And I still use parentheses, because I always use parentheses. Oscar, when you get that one, will you give it to me? Yeah, I already got it. Okay, what is it? 3. Okay, 0, 3. So we don't move from the origin, but we go up to 3. Next up is 1 squared plus 3. Ethan, when you get that one, will you tell me? 4. 1, 4. So from the origin, you go to the right 1, up 4. Okay, we only got 2 more. The next one is 2 squared plus 3. Patrick, when you get that one, tell me what it is. This one. 7. And because Patrick gave us the next one, I'm just going to fill it in now. So 2, 7, 3, 12. So I'm going to come down here and finish filling those in. So 2, 7, 3, 12. And hopefully you guys can now see the parabola that we made. He's a parabola because he has an x squared in his function. So just like on the previous page, we had a parabola and his function was x squared. This is still an x squared, so he looks like a parabola. If I make a line through the y-axis, you can see that he is symmetric. If you folded him in half, he would line up exactly. So last time we learned how to do this part here in the middle, plug in the value, and today we're relating that to graphing. So I want you to try this one now without me. And the numbers that I want you to plug in this time are a little bit different. So I want you to do -1, -2, -3, 0, -4, -5, -6. So I'm going to fill mine in, and then I'm going to come walk around to see how you're doing. Oh, this time your function is similar but different. So we still have a +3, but it's trapped inside with the x. So when I plug this in, what it's going to look like is -1 plus 3 squared. The next one would look like -2 plus 3 squared. Ugh. If you have all the points, you can graph them, or hopefully you can graph them. I'll come around the mountain and see how you do. Okay, we need at least another minute. Okay, let's go roughly 30. About 20. What was that? 10. Okay, so we should have another parabola with the vertex at -3, 0. Is that where your vertex is? Then you have -2 and 1, -1 and 4, and then 0 and 9. Then those are in the same position on the other side, and those coordinates match up. So we have this one, this one, this one. We draw our parabola, and he looks very similar. The only difference is now if I draw that line through the vertex where you can fold it and he matches up exactly, it's just in a different spot. So last time we learned how to evaluate functions. This time we're relating that to how we can use that to figure out what happens to a graph if we add something to it, what happens to a graph if we, or what happens if it's outside the function or if it's inside with the function. So that takes us to our function families page. So these are all the common function families, and we started with the most common one, which is the parabola. So our fill in the blanks at the top is a parent function is the simplest function with the defining characteristics of the family. So it's the simplest function in the family with the defining characteristics. So for the parabola, its defining characteristic is that it is shaped like a U and it is symmetric, meaning you can fold it in half at the vertex and the two sides will line up vertically. Parabolas either look like a U or they can look like a frowny. They can also be upside down. So this is the parent function. This is the simplest parabola that there is. And then these parabolas that we graphed are parabolas that are in the family. So this parabola has been moved up and this parabola has been moved over. This function family's name is the quadratic family. So this guy is the quadratic. Anything that looks like a U and is symmetric or looks like a frowny and symmetric is in this family. If all they do is give you a function, you are looking for the function that has a squared in it or an exponent of 2. Okay, the next function family is the cubic family. And it has that name because it is y equals x cubed, or y equals x to the third. So this function is a parabola whose leg, this left-hand leg, has been bent down. So a cubic function started as a parabola, and then somebody took this side and bent it down. The defining characteristics on this guy is he looks like a slide or a roller coaster. Anything that looks like this kind of slide or roller coaster situation is going to be cubic. If you're looking at a function only, you're looking for one that has a 3 as an exponent. Okay, anybody remember this guy? Starts with an A. Absolute value. This guy is absolute value. You've seen him as like this V. He could also be flipped or reflected like the parabola so that he looks like a triangle. His defining characteristic is that he's like pointy. He's a V or a triangle. His symbols are the straight lines or the gel cell for the X. For all 3 of these parent functions, notice that their vertex is in the same position. And the vertex is like the center or the beginning, for lack of a better word, of the function. So we have the U, we have the like roller coaster, and we have the V. This next guy I think is the weirdest one. So this guy is the square root function. He's y equals root x. And I remember him because I could like make a root symbol out of the graph. Like if I kind of change it a little bit, it looks like a root symbol to me. So the defining characteristic on this one is he's like a sideways parabola and somebody chopped off the bottom. So he was a sideways parabola and then the bottom is gone. He is the only function that has one arrow. In the set of families that we're looking at, he's the only one that has a point on one end and an arrow on the other. All of these other ones have arrows on both ends. Okay, we got 2 more. Number 5 is an exponential function. His family is exponential. He has arrows on both ends. He's the only one that has a vertex not at the origin. His vertex is at 0, 1. His defining characteristic is that he has one really flat side. So if I continued this part of the graph on, it's like very close to the x-axis. And then he has like a side that like shoots up so that it's vertical. So the defining characteristic on a exponent one is that it's like flat and then shoots up to almost vertical. He is y equals 2 to the x. Sometimes you might see it written as b to the x, or b for base. if you're looking for symbols on the last one, if the function has a root anywhere in it, he's a square root function. On this one, if the x is in the exponent position, he's an exponential. And the last one that we're talking about should be a new one. So all these other ones you should have seen in 10th grade. Maybe you didn't talk about the exponential so much, but this one, the inverse function, should be new. So his vertex actually isn't even touching the graph. His vertex is at the origin. And he's like 2 exponential functions. His symbols or his function is y equals 1 over x. So anytime you have a fraction and x is in the bottom, that's an inverse family. So those are our 6 function families that we focus on. So now if I zoom out, the next task for us is to identify what families these belong to. Half of them are looking at a graph and half of them are just looking at the function. So the first one, what are you guys thinking on this first one? Root, square root. Eight should be easy. What's this guy? Quadratic. He's the parabola. He's your parab. 9 is the cubic one. Okay, so for 10, 11, and 12, you're just looking at the symbols. Identify the symbols that are in the function and decide based off of that. I'm going to write in my answers and then I'm going to do one walkthrough just to verify that you tried these. Okay, so I'll come and walk through once. Okay, so 10 is absolute value, 11 is inverse, and 12 is exponential. You guys feel okay about that? Okay, next up is a discussion about how we get other functions in the family. So if this is a parent, where do we get all of the other parabolas that are in the family? Well, we have 2 examples of that right here. So this one, this first one on the left is in the family. The parent is usually down here at the 0, 0. So what we did was we took the parent function and we shifted him up by 3. So that his vertex is now at 0, 3. Instead of being at 0, 0, we moved him up. Well, what did his function look like in order to get that result? Well, it turns out that if you add a value to the function or you subtract a value to the function, it just moves that entire function up or down by that same amount. So it takes the parabola and moves the whole parabola up by 3. This guy, he has a parabola at -3, 0. So his vertex has been shifted to the left by 3. Well, how did we get this one? If I go up and look at my function, notice that it's still a +3, but it's trapped inside with the x. Whenever it is trapped inside, with the x, you do the opposite of what you see. So this actually ends up being left 3 instead of right 3, because when you trap it in there with the x, different things happen. So if you add it to the entire function or subtract it, it moves the whole thing up or down. If you have it in with the x, no matter what function you have, it's going to move it left or right, but in the opposite of what you see. So that should be vaguely familiar. And the other thing that should be vaguely familiar is this guy. How do we get the frowny, or how do we get the triangle? You get these by reflecting, and all you do is put a negative on the front of your function. So it takes this parabola and reflects it across the x-axis. Same with your absolute value. You do y equals with the negative on the front of the function. So y equals root x. Sorry, y equals negative root x. So hopefully that's all sounding vaguely familiar. Is it? Yeah, a little bit. Okay, let's flip to the next page. And we have like a crash course now in all the different transformations. So carrying on with that reflection, a reflection is when you flip the graph vertically over the x-axis. So this is a root function. This is the parent. It is y equals root x. Notice that the one next to it, he's been flipped over the x. We've just tipped him over the x. So he is y equals negative root x. Why did I put a root here when this was absolute value? Why didn't any of you tell me? Carly Ann! All these distance learners are probably thinking I'm a dum-dum. Come on. Those are straight lines. I need to be put in jail, not this x. The x is in jail, not in the root. Ugh. Now we need to start the whole lesson over. I kid, I'm not going to. Okay, so this guy, to reflect across the x, you flip it down. And then this one, he's different. This time you reflected him across the y. So he was over here and you flipped him over here. We don't talk about this one very much, but what he looks like is the negative trapped inside with the x. We only focus on this one. This is the one that we talk about the most. Okay, so that's our flipping it vertically. Now skip the dilate and let's go down to this other thing that we discussed. So here's my family. This is the parent function. It's at y equals x cubed. Okay, in this one, it looks like we're translating or moving the graph up or down. So a translation in this sense is shift the graph left or, oh, just kidding, up or down. I was just telling Carly Ann that I filmed this class period because it's the second time I teach it, so I make less mistakes. I jinxed myself. I did not make this many mistakes last period. Okay, so we talked about on this paper how if you want to move it up or down, it has to be outside of the function. So this guy is y equals x cubed. And then how much did I shift him up by? 4. So we just add 4. That's how you take a cubic function or any function and move it up. You add to the entire function. This guy we're moving down, so he looks like y equals x cubed minus 1. We moved him down by 1. So this guy up 4, this guy down 1. Our next translation is the left or right shift. So this is the one that's weird. He has to be trapped in with the x. To move it left or right, it has to be with the x. So what I have to write is a parenthesis, x, and then I do the opposite of what I see here. It has to be the opposite because it's trapped in there with the x. So if I went to the left 2 or went to a negative 2, I have to put a positive 2 in there with the x. And then I have to do the cubed. Very good. Because that's how you know that it's trapped with the x. Okay, so this one is similar. Y equals parenthesis x. Looks like we're at positive 5, so what do I need to plug in? Negative 5. And then we have to make sure we get that cubed on there so that it's clear this is the cubic function. So, depending on what teacher you had, you were supposed to spend quite a bit of time on this in Math 2, Secondary Math 2. So the only one that I've left off is the change in size. So when you dilate something, you change the size of the graph. You change the size of the graph. So this first one is our regular quadratic, y equals x squared. This middle one, often people think that we've made the parabola bigger or we've made him wider. And this one, we've made him skinnier or more narrow. So in 11th grade math, we call these a vertical stretch or a vertical shrink. This one is a vertical shrink. What the what indeed, because it's opposite. To me, this looks like we stretched out the parabola, but we're talking about the vertical change. So this is a vertical shrink. And I'm going to use Desmos to show you why. So on the computer side, I'm going to go to Desmos, and I'm going to graph a regular parabola. Then I'm going to graph a parabola that I'm going to make much wider. So let's do that guy. Okay. So I'm going to look at one point here. I'm going to look at 1, 4. So I'm going to type in 1, 4. 2, 4. Sorry about that. And he should end up being on our parent graph. So he's right here. So at 2 on the original graph, and I'm going to make this bigger once I plug it in. At 2 on the original graph, you're at 4. On this bottom graph, though, at the same point, 2, you're at 2/3. So now I'm going to make this much bigger so that you can actually see why it is called a vertical shrink. Notice that you went from being at 4 all the way down to being at 2/3. Is that making a little bit of sense? Zoom out, teacher. Can you guys see what happened there? Yes or no? This is your original. Once I put a fraction in front of it, it made it really wide, but then it also made it so that at the same point, the graph is much lower. On the original, it's 2/4. On the new one, it's 2 2/3. So this is why it's called a shrink, because it takes your point from being really tall to really short. We're okay there? Okay, you do that with a fraction. So even though he gets big, what you see on paper looks the opposite. It's a fraction. So this would be y equals 1/4 x squared. It's a fraction that makes it wider or bigger, and we call that a vertical shrink. So if this one is a fraction, that means that the vertical stretch has to be a whole number, and it's always that way. If you see a fraction, it's always a shrink. If you see a whole number, it's always a stretch. So this one is y equals 4x squared. So here, your size change was a 1/4 on the front of the function. Here, your size change was a 4 on the front of the function. And it's similar reasoning. So instead of 1/6, I'm going to change this to 6, and the new one gets really skinny. And I got to plug this in for 24. If I zoom out, you can see that the points get much higher. This is your original. This is your transformation. So we go from 4 all the way up to 24, and that's why it's called a stretch. If none of that graphing makes sense to you, then you're just going to memorize. If I see a fraction, it's a shrink, even though that seems weird. And if I see a whole number, it's a stretch. You're hanging in? Yes? Okay, let's put it all together. So we evaluated a function to make a graph, and those graphs were in the quadratic family. We've reviewed all the ways that we can change a parent function so that it's a different function in the family. So now we look at how we know what has happened to a function. So I have one more thing to bring you. We'll go through these problems and then you can do your quiz. And y'all need to sit up. This is not nap time. I've already given you the lecture about learning at home. Okay, so at the top of the next page, at the top of page 19, you see the vertex form. This is called vertex form for the quadratic family. These are the vertex forms for all of the function families that we've talked about. So I brought you a cardstock with all of the vertex forms, because I think it's helpful to see that all of them have the same things. All of them have the letter A, all of them have the letter H, and all of them have the letter K. And the only thing that is different is the symbols that tell you what family it belongs to. So this is telling me that it's a quadratic. This is telling me that it's a cubic. The gel cell is telling me its absolute value. The root tells me it's the root. This is in the exponential position. You might want to change that B to a 2. It doesn't matter that much, but you'll see it as a 2. And then the fraction and the X in the bottom tells you that this is an inverse. So I give you all of the vertex forms so that you can see the letters are all the same. You just have to identify what function you're changing. So let's go through and talk about what each of these does really quickly. This negative is whether or not you reflect. If there is no negative on the function, that means you didn't reflect it. So if there's a negative, that means you reflected it. Next up is the A. A. This is your vertical stretch or shrink. This is your vertical stretch or shrink. So remember, if this number is a fraction, you made it, you had a vertical shrink. If this is a whole number, it's a stretch. And if there's no number there, that means you didn't change the size at all. You didn't shrink it or stretch it. You kept it the same. Okay, your minus h, that's the weird guy. This minus here is why you have to do the opposite of what you see. That negative is telling you use the opposite. If there is a number trapped in with the x, this is when you shift left or right. So this is your left or right shift. If there is no number trapped in with the x, that means you didn't move it left or right. And then the last one we see here is the K. This is your up or down shift. If there's no number being added or subtracted, then you didn't move it up or down. And then just one last time to reiterate, whatever the symbols are tells you the family. I'm really exercising some very strong self-control right now. Because I want to be really salty. Elijah, hold it in. Okay, so now we have 4 different functions, 4 different families, and we're going to use this map, this information, to tell us what happened to the parent function. So the first one is a square root family. How do I know? Because it has a root in the problem. And now I move left to right. So on all of these, just start at the left and start writing down what you see. So this negative means I reflected it. So next to the 1, I write reflect. Then the next thing I run into is a fraction, which means that this is a shrink by 1/2. So I'm going to highlight this because there's a couple things happening here that you want to make sure that you notice because this is on your quiz. The first thing is I just keep it as a fraction. So I say a shrink by 1/2. Sometimes you'll see this written as shrink by 2. Whenever it is a shrink, you have to make it a fraction. So if it does say shrink by 2, you have to write it as 1/2. The other thing that I want you to notice is that I didn't put the negative on it. It's not a shrink by negative 1/2. It's a shrink by 1/2. The negative tells you to reflect. So moving left to right, I had the negative. I had the 1/2. I run into the symbol. That just tells me the family. And then trapped inside with the x, I have a positive 3. So am I going left or right? By how many? Left by 3. You okay on that one? Was on a yes? Okay, 2. What's your family? Quadratic, very good. And now moving left to right. There's no negative, so I didn't reflect, but I do have a 5 on the front, which means it's a stretch by 5. Then I have the symbol that tells me it's a quadratic. I hit the X, and trapped in with the X is a -3. So did I go right or left? Right. 3. Then I move outside of the X, outside of the function, and I add 7. So is that up or down? Up 7. Is that making a little bit of sense? Okay, you do that for numbers 3 and 4. Even this one, I know that it looks weird. I know that this looks weird, but just follow it from left to right. Do it exactly the same as we did the other ones. Okay, go. Where are you? Yes. On number 4, if you're moving left to right, which one do you hit first, the top or the bottom? Go another minute and then we'll check in. Up 30. Okay, let's check in on number 3. The parent is an absolute value. The first thing that you run into is the negative, so that's a reflect. Next up is the fraction, which is always a shrink of 1/3. There's nothing trapped inside the x, so you did not go left or right, but you did go down by 3. So reflect, shrink, and down 3. Now number 4, lots of you guys sit there and just don't even try it, but writing down something that's wrong is better than just looking at it and then laying down and dying. You guys have the skills that it takes to work your way through the problem. You go left to right. If you're doing that, the first thing that you would get to is the top of the fraction. It doesn't make sense to go to the bottom of the fraction first. In the top, you have a whole number of 5. So that means that you should have a stretch of 5. And that is the only thing that should have stumped you. Because down here, it's the same as all the other ones. You have a -1 trapped with the x. Anything that is trapped with the x is a left or right shift. So this one is right 1. And then you have a +3 on the outside of the function. That's the same as in all the other ones, so that's going to be an up 3. So the only thing on that one should have been that 5 in the top, making you go, I'm not sure what to do there. Last set is 5, 6, 7, 8. So this time it gives you the parent, but then tells you what they want you to plug in for the transformations. So I want to do 8 together. Let's jump all the way to 8 first. And once again, I'm just going to walk through this left to right. So I'm going to start with y equals. And then it tells me that I'm going to reflect it. So I'm going to put a negative. The next thing it tells me is a vertical shrink by 5. But I have to remember that whenever it says shrink, you must put it in a fraction. So instead of writing 5, I'm going to write 1/5. Then I know in this vertex form, the next thing that comes is the straight lines for the absolute value. So I do my straight line, I write x, and I see if there's anything that goes inside there. It says shift right 3, so what am I going to put in there, a plus or a minus? Minus 3. And then according to my vertex form, I write the straight line again. Then the last thing I check is, did I shift it up or down? I shifted up, so I'm going to say +2. So on these ones, if you need to, just work left to right in your vertex forms. So like on number 7, he matches this one. Sorry, I'll zoom out. Number 7 matches this one. So I'm just going to go through and check. I'm going to say g of x equals. Then the first thing I can check is it reflected or does it have an A? So it doesn't tell me to reflect it. It does say vertical stretch by 8, so I'm going to put an 8 here. And then on my card, it says that I have a little multiply symbol here, so I'm going to write multiply. And then I have a 2. I move up to the exponent position and see if they have me shift left or right. It says shift left, so up here with the x, what should I put? +1. So up there with the x, you put a +1. And then on my cardstock, it says I do k next, so that's an up or down. This one tells me to go down by 3/4, so I just do -3/4. So use that same reasoning to try 5 and 6. If you need your cardstock, just follow your cardstock left to right. I'll do mine and then I'll come and babysit. Okay, we're going to go one more minute. Write something down. Don't leave it blank. At the very least, write the vertex form. About 30. Okay. Let's check in. On number 7, I have -4 and then x squared plus 8. And I wrote my parenthesis on the x because I just followed this thing left to right. And when I realized there wasn't an h, I just closed the parentheses and kept going. You don't have to have them. If you have them, it's okay, but if you don't, that's also okay. Then on this one, all I'm doing is shifting this function down by 7. So that's like what we did at the beginning of class, so I just put a -7 on there. So hopefully, now with all of this together, this transforming functions makes a little bit of sense to you. So we started with evaluating functions, and then we talked about how you can evaluate functions to graph them, which leads into this big discussion about how do we move a graph around without having to, or how can we move a graph around without having to go in and calculate every single value or do a table every single time. Okay, so you have your quiz in Canvas. It's quiz 2-2. You have lots of time. So if you're sleeping when the bell rings, you're staying here. So take your nap now because you'll be doing your quiz after school. Do not be sleeping. And none of you have any excuse not to get this done. So make sure you're working.